Are you ready for an idea that will redefine the future of technology and your life? We are not talking about a faster computer. A quantum computer is not simply a more powerful version of your current device. Much like a light bulb is a different technology from a candle, not simply a more powerful one. It's an entirely new machine, based on the non-intuitive rules of quantum physics. It's 2025 and you're watching Future is Funny. This new computational paradigm promises to solve a specific class of complex problems that are currently impossible for even the most powerful classical supercomputers. It has the potential to transform sectors from pharma research to global finance. But how on earth does it work? And when will it truly change our world? Welcome to the era of the quantum revolution. It all starts with the smallest unit of information. In classical computers, you have the bit, a simple binary switch that can be either 0 or 1. A quantum computer uses a qubit. And this is where physics gets weird. The qubit harnesses the principle of superposition. Imagine a spinning coin. While in the air, it's not heads or tails, it's a fluid combination of both simultaneously. This ability to hold multiple values at once is a key source of a quantum computer's parallelism. But the real magic comes from entanglement. Entanglement is a phenomenon where multiple qubits become intrinsically linked. Once entangled, the state of one instantaneously influences the others, no matter how far apart they are. Albert Einstein famously called this spooky action at a distance. The result is profound. With just 300 entangled qubits, a quantum computer can represent more states simultaneously than there are particles in the observable universe. Superposition and entanglement are the tools, but how do they find the right answer? They use interference, cancel each other out, destructive interference, or just as water waves can add up, constructive interference, quantum algorithms manipulate probability waves. This process is cleverly designed to amplify the correct answer while systematically canceling out the probabilities of incorrect ones.
Only when you measure the qubit does its superposition collapse and give you the only final answer.
If you're wondering how this groundbreaking tech will impact your life, hit like and subscribe now so you don't miss our deep dives into the future. The true value of quantum lies not in replacing classical computers for everyday tasks, but in solving a specific class of problems that are currently intractable. For these select challenges, they are not just faster cars, they are entirely new vehicles, like boats, built to navigate terrain that is inaccessible to classical machines. The most immediate threat is to modern cryptography. The security of systems like RSA is based on one simple fact. It's extremely difficult for classical computers to find the prime factors of very large numbers. A famous quantum algorithm, Shor's algorithm, can factor these numbers exponentially faster. A powerful quantum computer could, in a matter of hours or days, break the encryption that protects everything from bank records to government secrets. This gives rise to the critical threat known as store now, decrypt later. But there's an incredibly positive side: simulating nature. Designing new drugs is computationally difficult because of the complexity of molecular quantum properties. Quantum computers could simulate these interactions with high precision, accelerating drug design from years to mere weeks or days. We could design novel materials from the ground up, more efficient batteries, new catalysts, engineering materials for more effective solar panels, and of room temperature superconductors, which would revolutionize the energy sector. Finally, Grover's algorithm provides a quadratic speedup for problems like finding the most efficient route for a delivery fleet or streamlining complex manufacturing. This impact is projected to generate up to $2 trillion by 2035 across key industries. The challenge is building this impossible machine. There is no single agreed-upon way. It's a global race involving several competing hardware approaches. You have the most recognized approach, superconducting qubits, used by Google and IBM. The iconic chandelier image is actually a powerful dilution refrigerator. It cools the chips to 15 millikelvin, a temperature colder than deep space, to minimize thermal noise. Others use photons or light particles, which are naturally more resilient to noise and ideal for networking quantum computers. Still others trap individual ions or neutral atoms using lasers or electromagnetic fields, giving them significantly longer coherence times, meaning they can maintain their quantum state for longer periods. Microsoft is pursuing the most ambitious path: topological qubits. The quantum information is encoded in the system's global topology, making it theorized to be inherently more robust against noise and environmental disturbances. Every approach faces one gigantic problem. Qubits are extremely delicate. The smallest disturbance, like a stray electromagnetic field or thermal fluctuation, destroys their quantum state. This is decoherence. Because noise is inevitable, error correction is essential. We cannot simply copy a qubit for redundancy. This is forbidden by the fundamental no-cloning theorem of quantum mechanics. The solution is to create a single, stable logical qubit by encoding its information across hundreds or even thousands of unstable physical qubits. This massive redundancy allows the system to detect and correct errors without disturbing the encoded information. This huge resource overhead is precisely why Microsoft's pursuit of inherently stable topological qubits is so strategic. It represents a potential shortcut around this Herculean problem by aiming to solve error correction at the hardware level. Are we there yet? There's considerable debate. More conservative estimates place the timeline for a commercially useful, fault-tolerant quantum computer at 15 to 30 years. But consider this: quantum computing is currently in the vacuum tube era of classical computing. Like the massive, error-prone machines of the 1940s, today's prototypes are highly specialized. Yet the direction of travel is undeniable. Billions of dollars in public and private investment are accelerating research exponentially. The quantum computer will not only grant us the power to solve previously unsolvable problems, but it will also provide a remarkable new tool, allowing humanity to probe the fundamental laws of nature and see the universe in an entirely new way. The quantum age is dawning. It's not a question of if, but when. And are you ready for this new world? Let us know in the comments below. And if you enjoyed this breakdown, be sure to share it with a friend and hit that notification bell. See you at the next technological revolution.